Welcome to The Explainer. Today, we're basically going to be digital detectives, uncovering the invisible, high-speed systems that keep our entire online world from just falling apart. It's a journey into data, danger, and the incredibly clever ways we protect it.
Okay, let's just start with something I know you've experienced. You're downloading a really important file, and you get that dreaded file corrupted error. Or you're on a video call, and suddenly the person you're talking to looks like a mess of blurry squares. What is actually going on there?
Well, at its very core, this is the culprit. All of your data, every photo, every email, every second of that video is just a long string of ones and zeros. We call them bits. And a data error happens when just one of those bits gets flipped during its journey from there to here, turning a 1 into a 0 or a 0 into a 1 and causing total digital chaos.
So to figure out how we fight this chaos, here's our game plan. First, we'll investigate the scene of the crime and see why these little errors are such a massive deal. Then we'll meet the two main types of errors. After that, we'll uncover the secret weapon our devices use to fight back. We'll see the detectives and fixers in action. And finally, we'll pull back the curtain on the invisible safety net that makes our digital lives even possible.
All right, let's jump in and look at the stakes. Why does one tiny flipped bit matter so much in the grand scheme of things?
You know, if you make a typo in a text message, it's whatever, right? Annoying, maybe. But in the digital world, that one tiny error can be a total catastrophe. A single wrong bit in a software program could cause your computer to crash. And just imagine a single bit flip in a bank transfer. It could literally change the amount from $100 to $1,000. In the world of data, perfection isn't just a goal. It's absolutely essential.
So now that we get the stakes, let's meet the villains of our story. Turns out there are two main types of errors that our data faces on its journey across the internet.
First, you've got what's basically the lone wolf, the single bit error. Take a look here. A sequence of data was sent, but on the receiving end, whoops, just one of those bits, a single 0, has flipped into a 1. Now, it's a tiny change, but as we just talked about, it can have enormous consequences.
And then you have its much more chaotic cousin, the burst error. This is a total mess. It's when a whole chunk of data gets scrambled all at once, usually because of some sudden interference or noise. Instead of just one bit flipping, a whole sequence of them changes, and that creates a much bigger problem to solve.
So, how in the world do we fight back against something that's literally invisible? Well, the answer is actually a surprisingly simple idea that we all use in our everyday lives.
The secret sauce is this one word: redundancy. I mean, think about it. You can't possibly catch a mistake if all you have is the original message, right? You have to send a little something extra along with it just to check your work. That extra info is what we call redundant.
This is a perfect real-world example. It's just like when you're spelling your name over a bad phone line. You say B, as in Bravo, right? That as in Bravo part, it isn't part of your name, but it's extra info. It's redundant, and it makes sure the other person gets a B and not a D or a P. Our computers do the exact same thing, just, with math instead of words.
And this is basically what's going on under the hood. The sender doesn't just shoot the data out there. First, it runs it through this special process, a generating function that creates a unique code, almost like a fingerprint, for that specific chunk of data. Then it sends both the data and the fingerprint. When your device gets it, it does the exact same math. If the fingerprint it creates matches the one it was sent, awesome, the data's good to go. If they don't match, nope, reject. Something went wrong on the trip.
Okay, so we know the secret is adding extra info. Now let's look at the two main strategies our devices use when they actually catch a potential error.
So, when a system finds an error, it really only has two choices, two paths it can take. Path 1, ask the sender to just send it again. That's called backward error correction. Or Path 2, try to fix the mistake itself, right then and there. And we call that forward error correction.
Yeah, the Ask Again method, also called ARQ, is literally the digital version of saying, sorry, could you say that again? The device spots an error and just pings the sender to retransmit that packet of data. Simple. But the Fix It Myself method, FEC, that's way more slick. It's like you heard a garbled word in a sentence, but you have enough context to figure out what it was supposed to be. It has so much of that redundant info that it can not only see the error, but actually pinpoint what the original bit should have been and just flip it back.
Now that say that again approach isn't always so simple. There are actually a bunch of clever strategies for it. Like one way is to stop after sending every single piece of data and wait for an OK before sending the next.
Another way is to send a whole bunch at once and then have the receiver just ask for the one specific piece that got messed up. It's all about making that resend process as fast and efficient as possible.
And just to even spot an error in the first place, systems use these really clever little math tricks. Take the parity check, for instance. It's super simple. It's like adding one extra bit to your data that just says, hey, the data I'm sending has an even number of ones. If the data shows up at the other end and it has an odd number of ones, the system knows immediately that something got flipped. These are the kinds of checks that create that digital fingerprint we were talking about.
But some codes are so advanced, they can actually do that forward error correction. They can fix the mistakes themselves. And the Hamming code is just genius. Here's how it works. It cleverly tucks in a few extra check bits into the data. Each of these check bits keeps an eye on a different, unique group of data bits. So if an error happens, the combination of which check bits get tripped up acts like a set of coordinates on a map, telling the system exactly which bit is wrong so it can be fixed instantly. It's amazing.
Okay, so we've waded through some of the techie stuff, but now let's bring it all back home and see why this matters to you, to me, to all of us.
I mean, every single time you stream a movie without it buffering, or send an email, or download a file, these error control systems are working their magic silently in the background. That seamless digital world we just expect, it's all built on this constant, invisible, lightning-fast game of check, double-check, and correct.
And the scale here is just mind-boggling. We're talking billions of times every single second. All around the world, these digital detectives are on the job, making sure our data gets where it's going perfectly intact. It's honestly one of the biggest unsung heroes of our modern world.
And that really leaves us with a big question to think about. We're sending more data faster than ever. We're moving into a world of AI, of quantum computing, a world where basically everything is connected to the internet. So how are these error correction systems going to have to evolve to keep up and protect that future? What does a perfectly sent message even look like in that world?